Exactly. Thank you very much for this very nice introduction. This work has been carried out during my internship in Math Team in India Sofia Antipolis in collaboration with Dr. Matthew DeRose and Professor Albert Goldbetter. So bipolar disorder is a psychiatric condition that is characterized by pathological mood cyclicity between manic and depressive episodes. Its prevalence in the general population is about 1%, and about 35% of bipolar patients have this mixed features specifier or mixed affective states, which is a condition that is characterized by the coexistence of manic and depressive symptoms during an episode of mania or depression. Only small steps have been made for the understanding of this disease, and the basic findings include immune inflammatory changes in the lipid network, as well as disruptions in connectivity between networks that control emotion and cognition. So this is an example of the data that we have to model. These are bi-monthly samples of mood scores from a bipolar patient. The orange line corresponds to scores in the questionnaire ASRM, which is a questionnaire about manic symptoms, and the purple line corresponds to scores in the PHQ-9 questionnaire, which is about depressive symptoms. So we see that we can easily mistake periodicity for noise and vice versa. There have been various modeling approaches for this disease. Some of the models that have been used are behavioral activation system models, discrete time random models, like discrete time Markov chains and autoregressive models, also two-dimensional models like two-dimensional Ornstein-Uhlenbeck process, which is stochastic differential equations, but also biological rhythms models, which are ordinary differential equations, and they make an implicit assumption of the existence of a timekeeping mechanism that could be correlated, for example, with the circadian rhythms. One of those models was particularly interesting. This model was introduced by Albert Goldbetter in 2010. It's a 4D model of a phenomenological 4D model of bipolar disorder. The two main variables are M and D. They correspond to the activation of neuronal networks that are responsible for manic and depressive symptoms, respectively. So M inhibits D and vice versa. And the intuition behind this comes from the clinical observation of antidepressive induced manic episodes. And also FM and FD are intermediate factors. They can be thought of as neuromodulators. So FM is produced by M and it inhibits M. FD is produced by D and it inhibits D. Here we can see an example of the time series of the model. Two important information that we can get is that in this time sliding window, judging by the slopes of the time series, we can see that M and D change faster than FM and FD, so we can hypothesize that M and D are fast variables, FM and FD are slow variables. Moreover, we can see that these rhythms consist of large amplitude oscillations followed by small amplitude oscillations. And these kind of rhythms are often referred to as mixed mode oscillations. And they could correspond in a way to the mixed affective states that we mentioned earlier. So the purpose of this project was to apply the slow-fast analysis on this model of bipolar disorder to uncover the mechanism of creation of these MMOs, to explore how changes of the values of some parameters change the regime of the system, and also to explore the effects of adding noise to this system. So time series in general are a key output of these models, and they could be compared with experimental data sometimes. But one of the advantages of using mathematical models to study complex phenomena is that we can visualize how one variable changes with respect to the other variables in the state space of the system. So here, if we plot the solution trajectory of the system, what we see is that it consists of two fast segments that are quasi-vertical and two slow segments that follow very closely this green surface that I will define later. Moreover, what we see is that in the transition from the upper slow segment to the lower slow segment, the transition is abrupt here, whereas in the transition from the lower slow segment to the upper slow segment, there is a turning of the trajectory here, and this causes a delay. So this delay, in terms of interpretation, could correspond to a delay in the transition from a state of depression, low manic values, to a state of mania, high manic values. And we will show that by changing the values of some important parameters, we can control the length of this delay. The way Albert Goldbetter originally calibrated his model, he used four small parameters, KC1 to KC4. And in order to exploit the multiple timescales that are present in this model, we introduced this epsilon, the time scale ratio parameter, equal to KC3 and KC4, and we rescale the equation of FM and FD, as you can see here. So when the time scale ratio parameter multiplies the right-hand side of the slow variables, we say that the system is written in fast time. Now, if we want to study the fast segments of the trajectory, the fast dynamics of the system, we can take the limit epsilon goes to 0, and essentially we freeze the slow variables, FM and FD, and we consider them as parameters. What we get is the fast subsystem, which is an approximation of the fast dynamics of the system. Now, if we want to find the equilibrium of the fast subsystem, we have to solve the system of equations m prime equals 0, d prime equals 0, and we would get this expression here. If we plot this on 3D, we will get the green surface that I have already shown you, that is called the critical manifold. Now, if we superimpose the trajectory of the system on this critical manifold, we see that there is a remarkable fit between these objects, and therefore our original assumption of two fast, two slow variables was indeed correct. Now, if we want to study the slow dynamics of the system, we have to introduce slow time tau equal t times epsilon. And we write our system in slow time parameterization. Now, epsilon multiplies the left-hand side of the fast variables. Now, if we take the limit epsilon goes to 0, what we get is the slow subsystem, which is an approximation of the slow dynamics of the system. So the slow subsystem or reduced system consists of two differential equations for FM and FD, and one algebraic equation F. So the differential equations are constrained by this algebraic equation. Moreover, when epsilon is 0, I have to mention also that this algebraic equation F is exactly the same that we used in order to plot the critical manifold. So when epsilon is exactly 0, the differential equations are forced to involve on the critical manifold. So the role of the critical manifold is twofold. It is the set of equilibria of the fast subsystem, as we mentioned earlier, but also the phase plane of the slow subsystem. Now, the fast dynamics of the system are hidden in this algebraic equation, and because it has to hold true for all time tau, we can differentiate with respect to time, and we will get this expression here. Now, you see that when the denominator goes to 0, but not the numerator, then the slow subsystem is not defined. And this happens on the folds of the surface, here and here. But there are some special points that also the numerator goes to 0 of the same order. And these points are called folded singularities. You can see plotted here. These folded singularities are responsible for the turning of the flow and the delay that we mentioned earlier. Also, this part of the trajectory corresponds to the small amplitude oscillations that I showed you earlier in the time series. So Kf1 is an important parameter because it reflects the level of M, which it achieves 50% of the maximum rate of production of Fm. And these are the time series of the system for decreasing values of Kf1. So as we can see, as we decrease Kf1, we increase the number of small amplitude oscillations. So we increase essentially the period of the MMO or the delay that we mentioned earlier. Now, if we want to study how changes in the values of Kf1 affect the regime of the system, we can plot the bifurcation diagram. We see that for low values of Kf1, the system is in a steady state that is characterized by low values of M. So by low values of M, high values of D, depression. So region 1 corresponds to depression. If we increase the values of Kf1, we have a Hopf bifurcation here that gives rise to limit cycles. And our system, as you can see from the time series, is in an oscillatory regime between mania and depression. So region 2 corresponds to bipolar disorder. Now, if we increase further Kf1, we are in another steady state, which is characterized by higher values of M, lower values of D. So region 3 corresponds to mania. It is interesting that for values of Kf1 in the transition between region 1 and region 2, as you can see from the time series, we have mixed mode oscillations with an intermediate state closer to depression. In the parameter space, they are organized along closed isolated branches that are often called isolas. Also, for values of Kf1 in transition between region 2 and region 3, again, we have mixed mode oscillations, as you can see from the time series, with an intermediate state closer to mania. In the parameter space, they are organized along open branches that are bound in each side by homoclinic bifurcations. And this could be indicative of a mixed state of very large duration. Now, if we take a closer look to the isolas that I mentioned earlier, we can see them plotted here. We can see that the first isola that is closer to the Hopf bifurcation corresponds to an MMO with one large amplitude and one small amplitude oscillation. The second isola corresponds to one large amplitude, two small amplitude oscillations, and so on. So for decreasing values of Kf1, we have an increase in the duration of the in the period of the MMO. Also, you can observe here that there are period doubling bifurcations. And I should say that this structure of the presence of isolas in period doubling bifurcations is very characteristic for systems that exhibit the behavior of mixed mode oscillations. As we said, these mixed mode oscillations with an intermediate state closer to depression happen because of the existence of this folding singularity, in this case of node type. But also the MMOs with an intermediate state closer to mania happen because of the existence of this folded node singularity that is located this time on the upper fold of the curve here. Moreover, we found numerical evidence of the existence of chaotic oscillations for a narrow range of values for Kf1, and the mechanism of creation of this chaotic regime is period doubling cascade. And This finding is in line with claims of chaotic patterns of mood variation in bipolar patients that can be found in the literature. Also, VM is another important parameter because it dictates the maximum rate of increase of M. And we want to see how the regime of the system is affected when we covary two parameters at the same time. And this is the two-parameter bifurcation diagram. So the black line corresponds to families of Hopf bifurcations. The red line corresponds to families of saddle node bifurcations. And if we want to visualize it better, we can imagine that for VM equal to 1, we can take a snapshot of the bifurcation diagram, and we would have the bifurcation diagram that we mentioned earlier. So we would have two Hopf bifurcations here and here, here and here, and two saddle node bifurcations here and here, and here and here. So what are the two important information that we get from this two-parameter bifurcation diagram is for which values of VM and KF1 we have this oscillatory regime between mania and depression, and the values lie within this black curve here and here. Moreover, for values of VM below the cusp, we do not have anymore the possibility of two distinct steady states that we mentioned earlier of mania and depression. Finally, stochastic noise is ubiquitous in biological systems. So we want to see how the addition of stochastic noise would affect this system. And we added these noise terms here and here. They are multiplied with sigma 1, sigma 2, which are of the order epsilon. So we have small noise. And we see that more or less the MMO structure is retained. So this is, as you can see from the time series and the phase plane. And this is in line with other work that has been done about the robustness of MMOs to noise. And although the minimal requirement for MMOs is one fast and two slow variables, what we did was that we deleted one slow variable. Now it's considered a parameter, and we added a noise term in one of the two fast variables. And again, we have this behavior of mixed mode oscillations that this time are purely driven by noise, as you can see from the time series and the phase plane. And again, there has been work in this area, as you can see in this reference. And in summary, what we did is that we applied the slow fast analysis in this phenomenological model of bipolar disorder that is based on the inhibition with auto-inhibition mechanism. We uncovered the mechanism of creation of these MMOs that can be correlated to mixed affective states. We investigated how changes in the values of parameters change the regime of the system. We show evidence of chaotic oscillations. And last but not least, we study how noise affects the robustness of MMOs, and we propose a minimal model that exhibits the same behavior, but this time the MMOs are noise-driven. I think this work is important because it introduces this set of mathematical tools to the neuropsychiatric community, and it could be used in the future for the analysis and control of more biologically plausible models of bipolar disorder. We could also derive information regarding the values of the parameters from the regime of the system. But also open questions still remain regarding the biological interpretation of the parameters of the phenomenological model and what would be the benefits of using stochastic dynamical systems theory to analyze the reduced model further. If someone has, someone is interested in more details, we have posted a preprint about that in bioarchives. And thank you very much.
So thank you. It was very interesting. And there are already 3 questions. So
okay.
there is a question in the chat, which I will read from Hadi. He says, very interesting work. How do you think we can come up with real values for the model parameters to fit on real patient data?
Yeah. Hello, Hadi. So yeah, that's a very interesting question. Yeah, we could fit. Well, we could feed our model to the data from the behavioral data that we have. As I showed you, maybe I should share again my screen. Okay, as I showed you, this is an example of the behavioral data that we have. Of course, we can fit our model parameters to this kind of data, but the thing is that we don't have a biological interpretation of these parameters. We do not know exactly what do they refer to, because this is a purely phenomenological model. And so the only thing that does is it tries to replicate these data. There is not a correspondence to real biological substrate. Yeah.
Okay, thank you. Also, Jonathan Rubin wanted to ask a question, so you can unmute yourself.
Thanks. I'm curious, like, why do you think you see the isolas in association with one of the families of MMOs, but not the other one?
That's a good question. So yeah, your question basically is, yeah, why in the parameter space they are organized in different ways? Mm-hmm. That's a very interesting question, but that I think it's worth exploring more about the reason why that is, but which I cannot answer right now. Yeah.
Okay.
Yeah.
You can email me in a month.
Yeah, of course, of course.
Thanks.